All right, so we're going to do balancing reactions where we take it from word form, we build them with our chemical formulas, the correct chemical formulas, and then we'll balance. So we'll do one together and we'll do one on our own. All right? So our first reaction is magnesium reacting with hydrochloric acid, and it produces magnesium chloride and hydrogen gas. Okay, so magnesium and hydrochloric acid. Tell me which of these four compounds are going to be our reactants. Yeah, Drew, what do you think?
Magnesium and hydrochloric acid.
These are our reactants, okay? They are listed first. So magnesium is just elemental, so it's just going to be Mg. Is magnesium one of our diatomics? No, so it doesn't need to be Mg2. It's just magnesium, okay? Magnesium by itself. Okay, it's going to react with, that means it's a plus sign, hydrochloric acid. What's our chemical formula for hydrochloric acid? HCl, yeah, we had that one yesterday. HCl, okay? Those are going to produce, which means we get the arrow. Okay, it's going to produce magnesium chloride and hydrogen gas. So what would be our chemical formula for magnesium chloride? MgCl. Okay, MgCl. Let's look at what our charge is here. If we want to combine magnesium and chloride, a magnesium is a +2, a chlorine is -1. So that means if we cross down our charges, our formula should be MgCl2. Okay, so we have to be careful when we see words. We can't just automatically think MgCl. We got to make sure that we balance that chemical formula. Because if we don't have this 2 there, it's going to make our equation impossible to balance. Okay. And then hydrogen gas, what's the last component then? What's our last product? H, and it has to be 2. Okay, hydrogen gas is our elemental hydrogen. Since it's one of our diatomics, we have to have H2. All right, so now let's try and balance here. We'll list our elements, everything we have. So we have magnesium, hydrogen, and chlorine. On the left, we have 1 magnesium. On the left, we have 1 hydrogen, and on the left, we have 1 chlorine. Do we agree? Okay, on the right, we have 1 magnesium, 2 hydrogens, and 2 chlorines. So how would you propose that we balance this equation? Jonathan, what do you think?
Put a 2 in front of the hydrochloric acid?
Yeah, exactly. 2 in front of the HCl. That on the left will change our hydrogen to a 2 and our chlorine to a 2. So this matches, and this matches. This is now a balanced equation. Okay. Do we see that if we wouldn't have corrected our chemical formula and not had that 2 there, it wouldn't have worked. We wouldn't have been able to balance. Okay, so we've got to make sure that our chemical formulas are 100% correct. We on the same page? All right, let's try the next one on your own then. Aqueous nitric acid reacts with solid magnesium and hydroxide. Solid magnesium hydroxide, to form magnesium nitrate and water. Okay, what does the aqueous here tell us?
It's mixed with water.
Yeah, it's just mixed with water. It doesn't change the chemical formula in any way. So we just need to find the chemical formula with nitric acid and magnesium hydroxide. Those will be our reactants. Magnesium nitrate is one of our products, and water is our other product. Okay, so let's get the chemical formulas into our equation, and then we'll start to balance. Let's look at building our chemical formulas. So if I have nitric acid, we talked about an ic acid coming from an 8 polyatomic ion. So it will be nitrate, which is NO3. We'll pair that with 1 hydrogen. Okay, our magnesium hydroxide here, magnesium is a +2. OH is hydroxide, and its charge is a -1. So if I cross down these charges and I have a 2 on the outside of a polyatomic ion, what do I also need? Parentheses. So it will be Mg, parentheses OH, 2. Okay, that's telling us that we need 2 of the entire hydroxide molecule. So that's going to form for us magnesium nitrate. If we know magnesium is +2 and nitrate is NO3 -1, we cross down the charges. we also must have Mg parentheses NO3, 2, and then we have water, which is H2O. All right? Anyone get those all by themselves? Okay. Then here's our balanced equation. A 2 coefficient in front of here. This gets left alone, and a 2 with our water. So now we're going to talk about different types of reaction. We've talked about how to balance equations. We're still going to continue to practice that because it's such an important skill. But we're going to talk about 4 main types of reactions, okay? The first of which is called a combustion reaction. Has anyone heard this term before, combustion? Okay, this is a combustion reaction. So this is when oxygen combines with what we call a hydrocarbon. Okay, a hydrocarbon is any compound that has this formula C to the something and H to the something. Okay, some coefficient, or C to the X and H to the Y. Okay, these are coefficient or numbers. They're subscripts, could be any number. Okay, these are called hydrocarbons. Anything with that specific template of a chemical formula is called a hydrocarbon. No matter what the number is here, what number X and Y are, the products of this reaction will always be CO2 and H2O. Okay, so it will always form carbon dioxide and water. So it will look something like this. This would be an example of a combustion reaction right here. Okay, so C10H8 plus 12O2 will form 10CO2 and 4H2O. Okay, that would be an example of our combustion reaction. Here's our hydrocarbon. Here's our oxygen gas. It forms carbon dioxide and water. Okay, that's called a combustion reaction. So you'll have to know these 4 types of equations. So whenever you see this hydrocarbon with oxygen, that forms a CO2 and water molecules, that's going to be an example of a combustion reaction. Okay, so as you're balancing equations, you're going to have to start determining what types of equations those are, what types of reactions those are. All right, our next type of reaction is a synthesis reaction. Okay. What does it mean when you synthesize something? Do you know what that root of that word means? Okay, something synthesized is not natural, it's made. Okay, right? You make something. So synthesis is when 2 or more simple compounds combine into one complex molecule. Okay, so you start with 2 or more things, you only end up with one product. So you only have one product. Okay, so it will look like this. That's our template equation. And here's an example of an actual equation. Okay, so in our template or our base equation, we have some compound A forms with some compound B and forms some element A bonds with some element B to form a compound AB. Down here we see iron bonds with or reacts with sulfur to form this molecule, which would be called iron 2 sulfide. Good. Iron sulfide. So this is a synthesis reaction. Something is made. Okay, something is synthesized. Next is our decomposition reaction. What does it mean to decompose? If something is decomposing, what's it doing? Yeah, decaying or breaking down is what I'm thinking there. Okay, if something decomposes, it breaks down. So this is when a complex molecule or a compound breaks down into one or more simple compounds. So this is the opposite of a synthesis reaction. Okay, so a real-life example of a decomposition reaction would be if water molecules are broken down into hydrogen gas and oxygen gas. Okay, this is a decomposition. If you look at our template equations, you can see these are opposites. Synthesis and decomposition reaction are opposites. Okay, they do the exact opposite thing. Decomposition breaks down that single molecule, and synthesis reaction builds into that complex molecule. Okay, so for decomposition reactions, you'll only have one reactant. For synthesis reactions, you only have one product. Okay. The equation is called a single displacement. This is when one element trades places with another in a compound. One thing is displaced, okay, is moved around. So here's our base or our template equation. A plus BC, so this would be a compound with two elements. So one element reacts with a compound that has two, and then they switch places there, so it becomes AC plus B. Okay. All right, so in our single displacement, we start with an element and a compound. Then our element takes on a new compound with it and leaves one of the elements behind. Okay, so this is a single displacement. One thing trades places here. Okay. You don't have to write this part down. We're just explaining what happens here. Okay, that doesn't necessarily need to be written down. It's just explaining. Okay, so a double displacement is going to be just like a single displacement, except we switch both the cations and both the anions from our compounds. Okay, both the anions and the cations switch places. They take on the new partner. Okay, so A plus B, A and B react with C and D to form A and D plus C and B. Okay. Remember that in all chemical formulas, we list the cation first, right? Sodium chloride, magnesium oxide. So this would be the cation, this would be the anion, cation and anion. So when we switch places, it makes sense that this cation will go with this anion will go with that cation. Okay, so we get AD plus C and B. Okay, and that order will always be the same, right? There will always be a cation there. There will always be an anion there. Always a cation listed first, then an anion. In a double displacement reaction, they will combine just like that. Okay, so here's an example of a double displacement. Lead nitrate reacts with potassium iodide to form lead iodide and potassium nitrate. Okay, both the cations and the anions switched places here. So lead was our cation, nitrate was our anion, potassium was our cation, iodide was our anion. If we do our arrows just like we looked, lead should be combining with iodide. Potassium should be combining with nitrate. Is that what happened? We got lead iodide and potassium nitrate. Okay, it will work like that every time in double displacement reactions. Okay.